Hi folks, welcome to this lesson in the P4 topic. I think it's about lesson 5 or something like that, and it's all to do with hazards and uses of radiation. So I want you to be able today to describe the dangers and uses of ionising radiation. There's a couple of objectives there for you, a couple of outcomes for you, sorry, and that is to describe radioactive contamination and also explain how radioactive traces can be used. There's a starter task there that I want you to have a bit of a quick think about, and it's based on the previous lesson. So it's just describe what half-life is, and then I want you to think about, do all radioactive substances have the same half-life? So just have a quick think about that. There's some key words there as well that we're going to be using in the lesson. So hazard, radioactive, contamination, and tracer. If you're not sure about what any of those words mean, give them a quick Google now. So just pause the video, 60 seconds, can you answer this starter task? Okay, so let's go through that then. So describe what half-life is. Half-life is the time taken, so the actual unit of half-life is time, is the time taken for half of all of the radioactive nuclei in a substance to decay. So if I started off with a lump of, let's say uranium, because that's a really common one, if I started off with a lump of uranium and it had 1 million radioactive nuclei in it, the half-life would be the amount of time it took for those 1 million nuclei to decay, half of them to decay, until there's only 500,000 left. Okay, so that is what the half-life is. And what will happen is, if you undergo one half-life, half of all the radioactive nuclei decay, another half-life goes by, and the amount that was left would decay by 50% again. Okay, so you'd end up another half-life later, you'd have 250,000 radioactive nuclei left. Do all radioactive substances have the same half-life? No. So there's some that have half-lives of like less than a second, and there's some that have half-lives of like billions of years, and there's all sorts in between those two numbers as well. So no, they don't have the same half-life, and as you'll find out later on, because we'll talk about the uses of ionising radiation as well as the dangers, that's important. The fact that there are radioactive substances with different half-lives is important. We've got different uses for those different half-lives. So yeah, we'll jump straight into it. So are all types of radiation ionising? Let's have a quick think about that. We've talked about what radiation is. We've talked about what ionisation is. So you should have an idea what ionising radiation is. Are all types of radiation ionising? The answer that you should have in your head now is, well, no. Okay, so radiation just means energy is being emitted from something, and it could be a wave, it could be a particle, and there's loads of different types of radiation, and they're not all ionising. So let's just have a look at 3 that we've been using so far. Alpha, beta, and gamma, all ionising. So yeah, they're all ionising radiation, but not all radiation is ionising. So let's have a look at a couple of types that aren't. So infrared, for example, this is a TV remote. You've probably seen on your TV remote, there's a little LED at the top, and you press a button and it doesn't come on. Well, it does come on, it's just that your eyes can't see it. If you use a phone camera, so if I was to pick the phone up and turn the camera on and look at a TV remote and press a button, your phone camera can actually pick up infrared, so it looks a little bit like that. So infrared is not ionising. There's no danger. I can't point a TV remote at someone and keep pressing the button and cause any kind of harm to that person because infrared's not ionising. Visible light is not ionising as well. That's a type of radiation. It's a type of energy that's being emitted, isn't it, light? And it's not ionising, which is a good thing because we're subjected to it every day, aren't we? So no, not all types of radiation are ionising. This is quite a nice little map here. It doesn't have any units, but all this is showing you is comparatively what the levels of background radiation are like in the UK. Okay, so have a look at that, and you can see there's something that stands out there dramatically, and it's this area down here, so like the Devon and Cornwall area. We'll talk about why that is in another lesson, I think, or in fact I'll just mention it now. It's all to do with the makeup of the rocks, so geological makeup of the rocks. So certain rocks like granite release a gas called radon, which is radioactive, and you get a lot of granite down in Devon and Cornwall, so therefore the background radiation is higher than it is anywhere else in the country. Up in Scotland you can see it's got comparatively quite a low level of background radiation. It's because there's less granite up there, that's all it is. Okay, so quite a nice little graphic there. Okay, so increased radiation levels increase the probability of illness and death. I don't know if you've seen, you've heard about, first of all, Chernobyl. There was a TV series on it not long ago on Sky, which is brilliant, well worth watching if you've not seen it. But the impact of that, of the kind of fallout, if you like, from the nuclear radiation after the reactor exploded is enormous. You can't fathom how much damage it actually caused. And I'm not just talking about the initial explosion, I'm talking about the actual radiation after the fact. So it increases the probability of illness and death. It can cause cell death or promote mutations which lead to the growth of cancers, which we'll talk about a bit more in a second. But the idea is the cells in your body absorb one of the types of ionising radiation, and that can cause a mutation, and then that could end up doing one of a few different things. Okay, so again, that is something for another lesson. I just want you to be aware of it in the meantime, though. So mutations take place in the structure of DNA. However, cells are often able to repair damage if the dose of radiation isn't too high. We're pretty good as humans. Our body is pretty good at dealing with radiation in certain amounts. So right now, for example, you're being bombarded by like cosmic rays and background radiation from the ground and soil around you. Your body puts up with that on a daily basis, and quite often it can just fix whatever damage has been done to cells. Or, if push comes to shove, if your body can't fix a cell, it just gets rid of it, destroys the cell, and then a new one just pops up and takes its place. So it's important to note that we're surrounded by background radiation. Let's have a quick look at the effects of radiation, and I want to introduce you to the unit that we're going to be measuring this in. So radiation dose is measured in sieverts or millisieverts. So this is how much radiation's actually been received. Okay, so let's have a quick look at some of these numbers. So we're interested in these to start off with, and you can see that a return flight to Geneva or 1 year dose from the nuclear industry is equal to roughly 0.001 millisieverts, minuscule amount. 1 year dose from nuclear weapons testing. So nuclear weapons testing releases ionizing radiation into the surroundings, into the environment. 1 year's dose of that is equal to about 0.1 millisieverts. Now, I'm not saying if you're stood next to a nuclear bomb that goes off, you'll be fine. I'm talking about in general, around the globe, the amount of background radiation that's attributed to nuclear weapons testing. If you were subjected to that amount in a year, that's how much you'd get. A 1 week holiday in Cornwall, now that's interesting, isn't it? That's slightly above 0.01 millisieverts. You actually get, sorry, is that 2? That's a 2, isn't it? Oh no, it's a 1. A 1 week holiday in Cornwall actually subjects your body to more radiation than a 1 year dose from nuclear weapons testing. One chest x-ray is about 0.1 millisieverts. 1 year dose from natural background is about 0.001 sievert. Important to note, we've gone from millisieverts to just sieverts. So that's our 1 year dose from natural background. And you can see all of these are pretty standard things, and it also says no human health effects. So in the long term, all of these things aren't really going to have an effect on you. Your body can cope with those, that's fine. That's kind of natural background radiation that our bodies can cope with. But then as you get higher and higher up, you get to about 1 sievert, and that's when you start getting problems. Okay, so early effects, meaning you could die from this literally straight away. Straight away is the wrong way to describe that. I mean, if you were subjected to 1 sievert of radiation, you would have radiation poisoning, which could kill you quite quickly. But then the late effects, so there's some evidence of increased cancer incidence. If you get a dose around here and above, you could end up getting cancer because of it. Now, this guy was I think he was a Russian spy that defected to the UK. His name's Alexander Litvinenko, and he was given a dose of 1 sievert, which proved to be fatal. So he had a 1 sievert dose of radiation. So he received a radiation dose of 1 sievert, and it proved to be fatal. I think they put it in his tea or something. So some Russian agents came over to, I think it was in the UK, came over to the UK, put some radioactive substance in his tea, he drank it, and he got about 1 sievert dose, and it killed him. It killed him. So he was a Russian spy that defected, and that's what happened to him. Not very nice, really. Right, so I'll read this through because I know it's a big block of text. Radioactive contamination is the unwanted presence of materials containing radioactive atoms. So unwanted presence is the key there. They can be on surfaces or within solids, liquids and gases, including in the human body and on the skin. Radioactive materials in the environment, whether natural or artificial, can expose people to risks. And radioactive materials are marked with a hazard symbol. Now, you can't see the figure there, but I'm sure you've all seen a radioactive hazard symbol before. It's kind of like black dot in the middle with 3 black things around it, and that tells you that it's radioactive. You see that, don't go touching it, okay? Don't go near it. And we do have, in school, radioactive sources. We use them in practicals. We get them out and you can see them. But there are also like really strict rules that we need to follow to make sure that everyone's safe while we do such a thing. Okay, so for example, the place where they're stored can't be within 2 meters of 2 meters, 5 meters, I can't remember that number, but it can't be within a certain range of where someone normally works. So I couldn't just like have them locked up next to my desk at school because I'm right near them, and therefore the radiation might be able to penetrate through the box and get to me and do some damage. We also have to be really strict in terms of like signing them in and signing them out. So when a teacher's using them, we need to know what time they're using, we need to know what class they went into, how long they were in there, what they were used for, and then they need to be signed back out into the protection, if you like, of the lab technician. So we need to be really careful with them. Contamination occurs when people swallow or breathe in radioactive materials. Radioactive materials can also enter the body through an open wound or be absorbed through the skin. some radioisotopes may be absorbed by specific organs where it's possible they could cause cancer or mutations of genes. So this is really just talking about the effect of contamination. It doesn't say here, by the way, you could be contaminated by a radioactive substance and it not be inside, it could be on you. So for example, if you go to Chernobyl, one of the big problems is, it's not the fact that the amount of radiation that you get subjected to while you're there, it's that if I was just to wander into Chernobyl now, I'm going to have a look round and have a nice time, and then come away, some of that stuff, some of that radioactive material that was might be just floating around in the air, might have landed on me, and then I'm walking off and I'm taking some of it with me. So now I'm consistently being subjected to the radiation that's already on me. Okay, so have a quick think about these two questions at the bottom. Just pause the video if you like, have a quick read back through there. Okay, so let's have a quick look at that. What is radioactive contamination? Well, it said it up here. Radioactive contamination is the unwanted presence of materials containing radioactive atoms. So if you've got something that is radioactive and you either don't know it's there or didn't want it there, it's on you or it's in you or whatever, that would be classed as radioactive contamination. Why is contamination a hazard? Well, that's discussed down here. So some radioisotopes may be absorbed by specific organs where it's possible they could cause cancer or mutations of genes. That doesn't even need to be absorbed by specific organs. If you're subjected to a large enough dose, whether it's internally or externally, you could still get mutation of genes and possibly cause cancer or cell death. So it's not something to be underestimated, contamination, especially considering a lot of the time you can't know that you're even contaminated. So we've not got like a Geiger counter on us that will say, oh, you're contaminated. You won't start feeling ill until you're really ill. So we need to be extremely careful when we're dealing with anything radioactive, basically, because, well, we can't see it, can we? So protected against radiation, then, it is, for some people, unavoidable to have to deal with nuclear radiation. So, well, they're good saying, oh, just keep away from it. But what about radiographers or nuclear technicians? They're around it, and, well, they need to be protected, okay? So you can see what they're wearing here. They're wearing kind of like aprons. Those aprons are lead-lined. So they'll weigh quite a lot, but it's necessary to block some of that radiation and make sure that the dose that they're receiving on a daily basis stays within safe levels. This, you can see there's a radioactive, so this just looks like a pile of bricks, but what it actually is, each of these is a lead brick, and inside that kind of cocoon of lead is a radioactive source, okay? So that is being done to try and prevent contamination and prevent people being subjected to radiation that they don't really need to be, to try and protect people. So because of this, exposure is carefully monitored and radiation shielding is used to minimise their contact. This is called a dosimeter, and you can see there's a unit there that I introduced you a minute ago, and it says sieverts there. So we've got microsieverts per hour. Okay, so that is saying that every hour you're getting 0.1 microsieverts dose of radiation. Now these are really interesting because I don't know what the numbers are here, but I know there's like a government stated maximum that you can receive in like a day, a week, a month, for example. And I've heard stories, I don't know whether these are true or not, I've heard stories of people that work in the nuclear industry and they always have to wear one of these dosimeters, and the dosimeter is well aware of what your maximum is for a week. Okay, it knows that you cannot go above a certain amount in a week. So if you're working, let's say you work Monday to Friday, and it gets to Tuesday, and your alarm goes, well, hang on, you've gone above your weekly maximum, you need to leave right now, you'd have to leave. It doesn't matter that it's only Tuesday, you can't just keep on working. Your boss can't say, oh no, you keep working because you're here till Friday. Your boss goes, right, go home, come back next Monday, you still get paid for it, it's not your fault you got subjected to that amount of radiation. So these are really important. They're called dosimeters, as in measuring the dose of radiation that you're receiving, and anyone that works in any kind of nuclear setting will be using one of these. Important to note this bit, radiographers. For those of you that have had an x-ray before, you probably noticed that when it comes to the x-ray, someone comes out, a radiographer comes out and goes, right, sit here, position here, get your position set up right, and then the radiographer leaves. They don't stay in the room with you. They'll go and stand behind a screen, or they'll go into another room, or just leave the room whilst the x-rays are fired at you, essentially. Because although one x-ray is not that bad for you, a radiographer is there all day, every day, doing possibly hundreds of x-rays of people. That is a massive dose of radiation to be receiving. So to stay safe, they'll set you up, it's fine while it's not on, and then they'll leave, and then they'll take the x-ray whilst they're not in there, and then once it's finished, they'll come back in, and then that's fine. They've not been subjected to it, only you have in that situation. So people need to take care and make sure that they're not receiving too large a dose of radiation, essentially. So these radioactive substances can cause cancer, but they can also be used to treat cancer, or used in the treatment of cancer, I should say. So it could be applied internally, as you can see here. This darker part of the lung tissue is labelled as a tumour. So the idea is this person, obviously it's a diagram, this person's got lung cancer, And in order to treat that lung cancer, what they can do is kill those cancerous cells. Now, surgery in the lungs is obviously incredibly difficult. You can't just like open someone up and then cut open the lungs and then remove those cancerous cells. So what's being done here is a bronchoscope, which is just a camera that can go down into your bronchus, has gone down, and using a catheter, which is a way of delivering things, either in or out of the body, a radioactive source has been placed at the exact site where the cancerous cells are. And the idea is, it's a radioactive source that's got quite a small zone in which it acts, so it's probably an alpha source. And by placing it near those cancerous cells, it's going to kill those cancerous cells. It's subjecting them to a massive dose of radiation, which will kill off those cells. So that's a way that it could be applied internally. I should stress this is a bit of a sensitive topic because cancer is something that's affected pretty much every family. I don't think I know anyone that doesn't know someone that's been affected by cancer in one way or another, whether it's family or friends or whatever. So although it's a sensitive topic, it's also important that you learn about this. Okay, so we're nearly done with it anyway, so don't worry too much about that. So it can be applied internally, but it can also be used to form images. And you can see in this, this device over here, this is called a gamma camera. No prizes for guessing what it detects, gamma radiation. And in this picture, someone's been injected with a radioactive tracer. Okay, and a radioactive tracer just basically is something that is radioactive and gives out, in this case, it's going to be gamma radiation. And then the person that goes around the bloodstream. The person goes into a gamma camera, and the camera can detect gamma radiation and form images of inside someone's body without opening them up. So it's like really, really interesting bit of tech, this, and really useful for studying areas that would be difficult to get to, even from a surgical perspective. Right, so the use of radiation in hospitals is also important as a means to observing certain organs or affected tissues. So let's delve a bit deeper into what I've just started talking about. Okay, so in this situation, you can see the tracers being injected into a vein, and they could be injected, swallowed, inhaled. There's loads of ways that tracers can be used. And a tracer is just a way of, it's just a radioactive substance that is introduced into the body, either through injection or ingestion or inhalation, and then a device is used to observe radiation from the outside and basically draw pictures of what's happening on the inside. So you can see in this one then, so the tracer is then observed using a PET scan. There's loads of different things. I'm using a PET scan as an example here, and that's called positron emission tomography. As in, a positron is emitted and then pictures are built up based on those. Now what's really interesting to know here, it says right upper lobe lung cancer rate. These tracers are usually bound to like carriers. Okay, so that'll be molecules like glucose or something like that. And you use different carriers and different tracers for different parts of the body. So for example, if you were interested in the kidney, like you can see in this picture, someone's injected the tracer, which is attached to a molecule that the kidney metabolizes. So if I was to introduce this substance into the body, as it's passing around the bloodstream, the kidney goes, oh, I deal with that substance, you come in here. And as it gathers lots of that substance in there, you can see it starts to glow because there's a lot of that radioactive substance here. Now that's all fine, and if it wasn't for this glowing section here, that would all look fairly normal. The problem you've got is you can see that this kidney's glowing because kidney tissue absorbs the carrier that's been used and gives out a lot of light in terms of there's a lot of radiation being emitted from that point. That should only be happening in the kidneys, but for some reason there's some tissue in the lungs that's doing exactly the same thing. There's some what looks like kidney tissue in the lungs. That is what cancer is. And it's bizarre to think about it like this, but what actually happens is if you get cells that undergo mutation thanks to radiation, those cells a lot of the time end up turning into something else. So bear in mind that the cells in the human body are all very similar, and there's only certain instructions in the DNA that determines the difference between like a lung cell or kidney cell or brain cell or nerve cell. So by mutation, they could end up becoming something else, and in this case, some of that lung tissue has started to turn into kidney tissue. So you've actually got the wrong type of cell growing in a particular place, and at this point, it's shown that this person's got, unfortunately, has lung cancer. Why is it important to use tracers with a short half-life? So if you did the previous lesson I did on half-life, hopefully you did that extension work where I said go away and look at some different substances and their half-lives and why it's important they've got different half-lives. The reason it's important to use tracers with a short half-life is if this person came in for this test and I said I want to inject you with a radioactive tracer and then I want you to subject you to a PET scan, that's great, and it would probably be done very quickly. But if I use something with a half-life of like 100 years, for example, I've just injected that person with something that is going to be radioactive for longer than that person will be alive. In the long run, that's going to cause some serious damage to that person. We want to use something that allows us to see inside the body, but also doesn't last a ridiculous amount of time. So we'll use half-lives we'll use radioactive substances with quite short half-lives, sometimes minutes long. So the idea being It's made in the hospital, it's injected into the person, they're tested immediately, and by the end of the day, most of that radioactive substance has decayed, so they're no longer radioactive. So different tracers are used for different parts of the body, and you can see here, for example, if you were going to do a brain scan, you might want to use technetium-99. If you were going to do is that like the larynx, you'd use iodine-123, lungs, nitrogen-13 or oxygen-15. So there's loads of different tracers that can be used for different parts of the body, because it's absorbed, different parts of the body absorb different substances. And it says here, for example, iodine-123 is absorbed by the thyroid gland. Oh, it's a thyroid gland there. So iodine-123 is absorbed by the thyroid gland. So you inject that into the body and the thyroid gland's going to go, come over here, I deal with you, iodine-123, come over here. And then that'll gather a lot of radioactive substance in that area and allow pictures to be taken of it that are reasonable, that you can see stuff. So due to the short half-life, tracers are usually made on site and are administered hours or even minutes after production. So they'll use a device, which I don't even think I'm going to tell you about in this topic, but it's called a cyclotron, that makes those radioactive tracers on site. They can't buy them, because you imagine you wanted something that has a half-life of like an hour. If you was to order that from somewhere, by the time it arrives to you, it's probably all decayed. That's no good. So you need to be able to make those radioactive tracers on site, ready for whenever you want to use them. Right, quick, did you know? People who have been diagnosed using medical tracers remain radioactive for several days typically. They have to avoid too much contact with young children and pregnant women. Nuclear radiation is partly dangerous to bodies that are growing rapidly, particularly dangerous to bodies that are growing rapidly, such as an unborn baby. Okay, so that is a quick did you know there. Right, there's some questions I want you to have a go at, so just pause that. Don't spend more than like a minute or two on each, and then I'll get back to you in a second. Read the text. In fact, I'll read the text at the top first. Tracers move around the body in the patient's blood. As a tracer emits radiation, we can monitor where the blood flows to. Therefore, blockages in the blood flow can be detected. Once the patient has been monitored, the tracer is no longer needed. If the tracer remained in the body, it will continue to damage cells without being of any use. Therefore, it is important that we use tracers with a short half-life. So pause the video now. Quick go, minute on each, and then we'll go through. Okay, let's go through those. A doctor has a choice of 3 radioisotopes that can be used as a tracer. The half-lives of the isotopes are 6 seconds, 6 hours and 6 days. Explain which isotope the doctor should use. Should be the 6 hours one. 6 seconds is too short. By the time you've administered that, and got the person ready and got them sat in the thing, most of it's decayed and you're going to end up with very little in the bloodstream that's going to show you what you need to see. 6 days is too long. So, but this is basically 6 days is almost a week. So that's like saying every week the amount of radioactive substance in that person's body, the amount of radioactive nuclei decays by 50%. That's too long. That's going to do too much damage. It says over here, if the tracer remained in the body, it would continue to damage the cells without being of any use. So 6 days is too long. 6 hours should be about right. So the idea being that after a couple of days, most of it has decayed. Suggest what type of source of nuclear radiation is the most suitable for a tracer. So when it's talking about source, it means alpha, beta, or gamma. It's gamma. Okay, and the reason it's gamma is because that can easily, effortlessly, if you like, pass through human tissue and bone. That's not going to get in its way. So we can easily detect it using whatever we're going to detect it with. If you was going to use a source of alpha radiation or beta radiation, alpha is definitely not getting through human tissue and bone. Beta might, but again, you don't want something that might get through, you want something that definitely does get through, so we use gamma every time. Suggest how a tracer could be used to check for a blockage in a patient's blood vessel. Well, it said that up here, didn't it? So as a tracer emits radiation, we can monitor where blood flows to, and therefore blockages in the blood flow can be detected. So you can imagine watching it on a screen as the gamma camera picks up the tracer as it's passing through the bloodstream, and you see it going down, passing through something, then just boom, stops. It stops for a reason, probably because there's a blockage there. So we can use tracers to look up things like that as well, not just sources of cancer. Right, there's some uses of radioisotopes here that they're fairly self-explanatory, and I want you to have a go at this yourself. So just pause the video and give this a go. It's out of 14, so don't spend more than 14 minutes on it. In fact, don't even spend that long on it, because some of them are just like one-word answers. So pause the video, give that a go, and I'll get back to you in a second. Okay then, so some background radiation comes from natural sources and some is man-made. Write down 2 man-made sources of background radiation. So, oh, there we go. So some background radiation comes from natural sources and some is man-made. Write down 2 man-made sources of background radiation, and you should have got medical treatments, nuclear bombs, nuclear waste, any of those is fine. Nick needs to find a leak in his drain. He's got some radioactive liquid and a detector. Describe how he would use these to find a leak, giving details of the type of radiation and the results he would expect from the meter. So this requires a bit of thinking outside the box really, but if you've got these 3 points or something thereabouts, you'll have got this right. So you pour a gamma source into the drain, pour something in there that gives out gamma decay, gives out gamma radiation I should say. Then you test above ground with a Geiger counter, and as you go along the pipe, detecting, The leak is where the count rate increases. So if I'm walking down and all of a sudden I get a higher count of gamma radiation and I keep walking, it goes back down again, that little area that I've just passed is wherever the leak is in the drain. You don't need these word for word, by the way. As long as you've got something along those lines, you'll have got the mark. Radioactive isotopes can be used as thickness gauges. A paper mill uses radioactive isotope to keep the thickness of the paper correct. The detector measures the amount of radiation passing through the paper. What sort of source, alpha, beta, or gamma, should be used, and explain your answer. Okay, so you might be thinking, oh, you've got to use gamma so it gets through it. But bear in mind, the paper is not going to affect gamma at all. There will be no difference if it's thick paper or thin paper, so gamma is out of the equation, you can't use that. Alpha is stopped by paper. You literally wouldn't detect it at all on the other side, remember, it is the most ionizing and the least penetrative, so we're going to have to use beta. Okay, so beta would pass through it, but if it starts to get a bit too thick, the count rate would drop. Okay, so beta, so it can penetrate thin paper, but it's stopped by thick paper. And it says why you can't use alpha and gamma there, but I've basically just described it. What will happen to the count rate if the paper is too thin? It'll go up. So if I've got something that's giving out beta decay there, and I've got paper there, and all of a sudden the paper gets thinner, well, more beta particles are going to be able to pass through it, so the detector will detect more, so the number would actually increase. A source with a long half-life is used suggests why. Well, you don't want to keep having to pay to get more radioactive source for your paper mill, so it works for a long time and it's expensive to keep replacing the source. It's the same for smoke alarms. So alpha radiation is used in smoke alarms, and they use something with a long half-life because you don't want to replace your smoke alarm because the radioactive source has decayed to the point where it's stable and it's no longer radioactive. I've just given you the answer to the next question. An alpha source is used in some smoke detectors. Explain how this type of smoke detector works. Very similar to the paper mill. Okay, so alpha particles travel through the air. I've got an alpha source there, and it travels through the air and it's detected over here. Okay, but then smoke particles get in the middle and stop those alpha particles being detected over here, so the detector no longer receives them. And this is wired up to a little bit of simple circuitry that says if you don't detect radiation, set the alarm off. So as long as in between those two things, the alpha source and the detector is clear, the alarm doesn't go off. But then if something gets in the way, like some smoke ends up in the way, then this will go, oh, hang on, I'm not detecting any radiation, sends a message, and then the alarm goes off. How is radiation used to sterilise things in the food and medical industries, and what type of radiation is used? So gamma radiation is used so it penetrates all parts of the food and the packaging. We're going to do more on this next lesson, so don't worry if you didn't know the answer to that, because I've not talked about it today, but we will definitely do it next lesson. We'll talk about irradiation and contamination. So gamma radiation is used so it penetrates all parts of the food and packaging, and it damages the DNA in any bacteria and kills them. So you 100% have eaten food that has been subjected to gamma radiation before, and it is perfectly safe. It's not contaminated, it's been irradiated, and we'll talk about the difference between those two in the next lesson. Okay, that's it there, so hopefully that was useful. If you've got any questions, usual setup, ask whoever gave you this video, or ask me. Either way is fine. Okay, so hopefully that's been useful to you.